Welcome! In this video, we'll be solving a challenging equation for real numbers. Here is the equation we need to solve. At first glance, this equation looks incredibly complex. Cubing and raising terms to the sixth power would be a nightmare. Our main objective is to use a more elegant method to find the solution. By the end of this video, you will be able to solve complex equations by simplifying them with substitution and applying the powerful Arithmetic Mean-Geometric Mean, or AMGM, inequality. Our first step is to simplify the equation. A key observation is that several expressions are repeated. Let's highlight these repeated parts to make them easier to see. We have the terms 6x squared plus 1, 3x squared plus 1, and 2x squared plus 1. To simplify, let's substitute variables for these expressions. We'll let a equal 6x squared plus 1, b equal 3x squared plus 1, and c equal 2x squared plus 1. Now, let's rewrite our original equation using these new variables. The left side becomes a to the power of 6 plus 2 times b cubed plus 3 times c squared. And the right side becomes 6 times a times b times c. So our massive original equation is now much cleaner. A to the sixth plus 2b cubed plus 3c squared equals 6abc. This substitution is the first crucial step to making the problem solvable. It converts a complex expression in x into a simpler relationship between a, b, and c. We've transformed the equation into a to the sixth plus 2b cubed plus 3c squared equals 6abc. Notice the 6abc on the right-hand side. This often hints at the AMGM inequality. The AMGM inequality states that for any non-negative numbers, their arithmetic mean is greater than or equal to their geometric mean. For k numbers, that means their sum divided by k is greater than or equal to their product raised to the 1k power. The key is the equality condition. The arithmetic mean equals the geometric mean only when all the numbers are equal. We'll use this crucial property later. Let's divide our entire equation by 6abc. Since a, b, and c are all positive, because x squared is always non-negative, we don't have to worry about dividing by 0 or reversing the inequality. Distributing the division, we get a to the sixth over 6abc plus 2b cubed over 6abc plus 3c squared over 6abc equals 1. Now, let's simplify each term. The first simplifies to a to the fifth over 6bc. The second simplifies to b squared over 3ac. And the third simplifies to c over 2ab. This doesn't quite look like the standard form for AMGM yet. The numerators and denominators are complicated. Let's return to the equation before we divide it. The right side, 6abc, gives us a strong clue. We need to find 6 terms whose geometric mean is abc. This means the product of the terms should be a to the sixth, b to the sixth. So, we need to apply AMGM to 6 terms that will multiply to a to the sixth, b to the sixth, c to the sixth. Our goal is to make the left side of our equation a to the sixth plus 2b cubed plus 3c squared look like the sum of 6 terms. Let's rewrite the left side by splitting the terms. We can write a to the sixth over 6 plus b cubed over 3 plus c squared over 2. This is just a rearrangement. The next step is the real trick. We need to make 6 terms whose product is a to the sixth, b to the sixth. We can rewrite the b cubed term as b cubed over 6 plus b cubed over 6. We can do this because b cubed over 3 is the same as 2 times b cubed over 6. Similarly, we can rewrite c squared over 2 as c squared over 6 plus c squared over 6. Take a moment to see why this works. B cubed over 3 is the same as 2b cubed over 6, so we can split it into 2 terms. And c squared over 2 is the same as 3c squared over 6, which we split into 3 terms. Now we have 6 terms on the left side. Let's write them all out. So, we have a sum of 6 terms on the left side. Let's call these x1, x2, and so on. That is, x1 equals a to the sixth over 6, and so on for a total of 6 terms. The AMGM inequality states that the average of these 6 terms is greater than or equal to their geometric mean. So, their sum divided by 6 is greater than or equal to the 6th root of their product. Let's simplify both sides of this inequality. For the left side, notice the sum inside the brackets is just our rearranged left side, which is equal to 6abc. So the left side simplifies to 6abc divided by 6, which is just abc. Now let's work on the right side, the geometric mean. We'll combine the b and c terms. Inside the sixth root, we have the product. We can rewrite the product of the 6s in the denominator as 6 to the 6. Now we can simplify this sixth root. The sixth root of the fraction is the sixth root of the numerator divided by the sixth root of the denominator. This simplifies to abc over 6. This gives us a new, very important inequality. We've shown that abc must be greater than or equal to abc over 6. So, we've derived the inequality abc is greater than or equal to abc over 6. This inequality must be true for any real numbers x, and thus for any positive a, b, and c. However, we know that our original equation states that the left side equals the right side. This means that the AMGM inequality we just used must hold with equality. The arithmetic mean must be equal to the geometric mean. This is a critical deduction. The only way our equation can be true is if the AMGM inequality applies with equality. And what is the equality condition for AMGM? It only holds when all the numbers are equal. Therefore, the 6 terms we used in our inequality must all be equal to each other. This is the breakthrough. From this set of equalities, we can simplify further. If a to the 6th over 6 equals b cubed over 6, then a to the 6th must equal b cubed. If b cubed over 6 equals c squared over 6, then b cubed must equal c squared. So, we have a system of equations. A to the 6th equals b cubed, and b cubed equals c squared. Together, these imply that a to the 6th equals b cubed, which equals c squared. We have found a powerful relationship between our variables a, b, and c. We've established that a to the 6th equals b cubed equals c squared. Now, let's use the actual definitions of a, b, and c. Remember, a was 6x squared plus 1, b was 3x squared plus 1, and c was 2x squared plus 1. Substituting these back in, we get that the sixth power of 6x squared plus 1 must be equal to the cube of 3x squared plus 1, which must also be equal to the square of 2x squared plus 1. This is great. It means that 6x squared plus 1 to the 6th equals 2x squared plus 1 to the 2nd. Taking the square root of both sides gives us a simpler equation. This gives us 6x squared plus 1 cubed must equal the absolute value of 2x squared plus 1. Since x is a real number, x squared is non-negative, therefore 2x squared plus 1 is always positive, so its absolute value is just itself. This simplifies to 6x squared plus 1 cubed equals 2x squared plus 1. It's also true that 3x squared plus 1 cubed equals 2x squared plus 1 squared. Again, we can simplify this. Taking the square root of both sides, we get 3x squared plus 1 to the power of 1.5, which is not an integer. This path is less direct than the first one. Let's stick with the first simplification. 6x squared plus 1 cubed equals 2x squared plus 1. This equation still looks a bit tricky to solve. Let's look for a simpler path. We have an even more direct consequence of a equals b, b equal b quarter. If a, b, and c are positive numbers, and a to the 6th equals b cubed equals c squared, this implies that a, b, and c are all equal. Let's test this logic. If a equals sign b, then a equal b. But we know a equal bb, so b equal b, which means bb equals sign 1. And if b equals sign 1, then a equals sign 1, and c squared of 1. Since a and c are positive, we must have a equal sign 1 and c equal sign 1. So if a equals sign b, then a equals sign b equals sign c equals sign 1. So, the equality of a to the 6th, b cubed, and c squared is a sufficient condition to say that a, b, and c must all be equal to 1. This is a much simpler condition to solve. We have concluded that our solution requires a, b, and c to all be equal to 1. This gives us a system of equations to solve for x. We will set each of our original expressions for a, b, and c equal to 1. First, a equals 6x squared plus 1, so 6x squared plus 1 equals 1. Solving for x squared, we get 6x squared equals 0, which means x squared equals 0. If x squared is 0, the only possible real value for x is 0. So, from a equal sign 1, we find that x must be 0. Let's check the other equations to make sure they also give x equals 0. Second, b equals 3x squared plus 1, so 3x squared plus 1 equals 1. This gives us 3x squared equals 0, which again simplifies to x equals 0. Finally, c equals 2x squared plus 1, so 2x squared plus 1 equals 1. This gives us 2x squared equals 0, which once more leads to x equals 0. All three conditions are consistent and give us the same answer. Therefore, the only real number solution to our original complex equation is x equals 0. Let's quickly recap our solution to this challenging problem. We set out to find the real numbers x that satisfy this equation. Here is the equation we solved. First, we simplified the problem by using substitution. We let a, b, and c represent the repeated terms, which turned the equation into a plus 2b plus 3c2 equals 6abc. Next, we rearranged the terms to set up the arithmetic mean-geometric mean inequality. We did this by splitting the b cubed term into 2 and the c2 term into 3, giving us 6 terms in total. Applying AMGM, we found that the only way for the inequality to hold with equality, as our equation stated, is if all 6 terms are equal. This led to the powerful conclusion that a equals b cavet equals c cavet equals 1, which simplified further to a equals b equals c equals 1. Finally, we set our original expressions for a, b, and c equal to 1. Each of these simpler equations gave us the same result. X squared equals 0. The only real solution is x equals 0. Today, you've learned how to simplify complex equations with clever substitution and how to apply the AMGM inequality to solve problems that would otherwise be intractable. Thank you for watching.